We're going to pick back up in the middle of section 1.4. We're talking about something called continuity. Just a reminder of a few things that we had talked about last time. There are things in our everyday world that are continuous, but not everything. So we had some examples. In particular, the two examples from here that we had about continuity were the following object and the cholesterol levels. And then the bank account, of course, is not. It's actually called discrete. And there's an actual math class called discrete math that we teach as well about those kinds of functions. In particular, like mathematical definition, we said that continuity is this idea that the limit actually equals the function value at a particular point. Intuitively, we have this idea that we can draw the shape without actually having to pick up our pencil or something like that. And we had taken a look at taking a function that wasn't continuous at a particular place and making it broader to eliminate one or more of the locations where it had continuity problems. And in particular, the ones we had looked at were ones where there was like a hole in the graph. Okay? And that actually puts us at remark 4.1. There it is. All right, so for function f to be continuous, what this actual definition has said is it says three things. It says, first of all, f of a must be defined. That is, you must be able to plug in a into the equation. Well, that's exactly what couldn't happen at a couple of locations in the previous problem. You did not have the ability to plug in the number 1 or 2 or something like that because you got denominators of 0. So you have to have the ability to plug a value in. The second thing is the limit has to exist. That is, you have to be able to get close to the value from both sides of that x value. The limit has to exist. And the third thing is that the limit and the function value have to be the same. So this is the three things that are actually sort of embedded inside of that definition of continuity that we did last time. Okay, all three of these things. So what we're going to do now is we're going to take a look at a function and we're going to decide if it is continuous based on these three criteria. All right, so our function that we're looking at, number 3, is f of x equals x over x minus 1. And this directions actually tell us to explain why each function fails to be continuous. So they actually told you something about it that's really important. They told you this is not going to work. And your directions are to figure out why not. Which of those three criteria, and maybe there's more than one, it actually fails to have happen. All right, so the remarks for 4.1 say that we have to have it defined. The limit has to exist, that is the limit from both sides. And they actually have to be the same value. So we're just going to kind of go down the list and see what, if anything, and we know something, will fail. So the first issue is, does the function value exist? And in particular, they care about the value at x equal 1. So our question is, what is f of 1? And it's undefined. Why? Yeah, we get that 0 in the denominator, right? So if you get a 0 in the denominator, we call it undefined, and what we mean is that it doesn't exist there, right? So f of 1 does not exist. And you can write down lots of things. D and E would be one of them. You could say is undefined. You can say, in particular on this one, it has an asymptote there. You might not actually know if it's an asymptote or a hole. This one is an asymptote. But it does not exist. I do not have the ability to plug in x equal 1 into my function f. All right, so it fails condition 1, right? Because condition 1 says I have the ability to plug it in, and we just found out that we don't. We do not have that ability. Now, in the effort of saving you a little bit of time, I'm going to sort of give you a freebie on number 2. I mentioned already that this function has an asymptote at this particular point in time. If we were to graph this, which would be a good thing for us to actually do, the graph around x equal 1, here's my 1 value, and of course your calculator doesn't put these dotted lines in, but some of them actually fill it in. But the graph actually would look like this. Hang on. Get it as close as reasonable as I can. It looks something like this. So we've looked at these from a graphical standpoint, and we could do it from a numerical standpoint as well, plugging in numbers nearby to x equal 1 into a table. But if we come at this thing from the right-hand side, that is, we're moving from the right toward my x equal 1 value, what value are we getting close to on the y-axis? Infinity. We're going up forever, so we're sort of approaching infinity. And if I approach this x equal 1 value from the left, from the left-hand side of the graph, I'm moving toward it. What value am I approaching on this side? That's negative infinity. And do they match? No. So this would also be that the limit doesn't exist. So the limit as x approaches 1, and it's from both ways, of my function doesn't exist. So this fails 1 and 2, which automatically means it's going to fail 3. It can't pass 3 if it doesn't pass 1 and 2, because 3 says that the first two work and they're equal. Well, the first two didn't work. So by default, this one also fails. So it sort of fails because 1 and 2, really what that is they don't match. And of course, they can't match if they don't exist, right? They don't match, though. So this one is a royal failure. It fails every single possible place. And it wouldn't have to fail every single place, right? If it fails at least one of these places, we're going to not have it working out for us. But this one fails royally. All right, let's take a look at what happens when we have polynomials. We've talked a little bit about polynomials with limits before in the last section, so we're going to talk about polynomials with continuity now. So all polynomials are continuous everywhere. We said they had limits everywhere before, so they're continuous everywhere. Additionally, so are sine and cosine. And so is the nth root of x. So like square roots, cube roots, fourth roots, things like that. As long as, and it works anytime that n is odd, so cube root, fifth root, seventh root, okay? And then it works anytime n's even as long as you have positive values underneath the radical. So you're only looking at the x is greater than 0 values. And we talked about that from a limit point of view before. So all this does is it expands all of those limit issues that we had in the last section to tell you the same thing's true about continuity. If it works for limits, it's going to work for continuity in this particular regard as well. Theorem 4.2 does the exact same thing for addition, subtraction, multiplication, and division of functions. Again, we saw that happen in 1.2 about limits. When do limits of these things exist? How does that work? How can I find these limits? Well, I can add, subtract, multiply, and divide. And the same is true, this is telling me, for continuity. So if we have f and g continuous at x equal a, then all of the following are continuous. The sum, the difference, that's number 1, the multiplication, and then the division as long as the denominator is not 0. We're going to see that also. That crops us all the time. There's this extra condition when we have denominators. Now there's one more, Theorem 4.3. And Theorem 4.3 says the following. Suppose that the limit as x approaches a of g of x is L, and f is continuous at L. Then the limit of f of g of x is f of the limit of g of x equals f of L. So write it down first if it's not already written on. I think there's a blank for all that sort of that long equation there. And then let me talk about what that actually says. Okay? So the limit as x approaches a of f of g of x equals f of the limit of g of x. And since the limit of g of x is L, that's f of L. Okay, so what this does is it gives me the ability to put a function inside of another function. And pardon me for going a little bit out of order, but if I skip to the example, I think it'll make the most sense. So I'm going to go over here to example 4 and show you what it means, what we just did means in terms of this example. So this example says the cosine of 1 over x. Well, over here it said that cosine of x is continuous, right? It also says down here on part 3 that 1 over x should be continuous as long as the denominator is not 0. Well, what this is doing now is it's putting the 1 over x inside of the cosine function, right? That's what that theorem says. It says that I can embed one function inside of another one. So maybe you put a polynomial under a square root. Or in this case, you put a rational function inside of a cosine. So all we're doing is saying that we have the ability to put one function inside of another one. And that is really all that this theorem says right here. And the corollary says the same thing in a slightly different way. It says, suppose that G is a continuous at A, okay, and F is continuous at G of A. Then the composition F composed G is continuous at A. And if you'll remember, this F, the little circle G, is the same as saying F of G of X. That's what that notation means. F little circle G means F with G inside of it. So all this is saying is that if I have a continuous function inside, right, so if G of X is continuous, and I plug it inside of the function F that's also continuous at that point, that I have all the same continuity theorems that I had before. Okay? So let's take a look. There's one more about interval continuity. All of the continuity theorems up to this point have said continuous at a particular point, continuous at L, continuous at A. And then we have a few things that say continuous everywhere. Here's continuous at A. You notice those notations? Well, this one actually says that we can do it on an interval. It doesn't have to be at just one place. So if F is continuous at every point on the interval AB, so that's not the point A, like it's not an XY ordered pair. It starts at A, it ends at B. So some list of X values, some interval of X values. If it's continuous everywhere in between those, then we say it's continuous on that interval, that whole place of location. And if it's also continuous at the endpoints itself, then we use those square brackets. Those square brackets simply mean that the endpoints get included. And finally, if it's continuous on the entire number line, from negative infinity to infinity, we call it continuous everywhere. So if there's no interval specified and it just says continuous, we mean continuous everywhere. So there's just some notational kinds of things that we use kind of loosely sometimes. And this is sort of identifying the pieces and how they go together. Any questions before we look at an example of one? Okay, I see a few of you still writing, so I'll pause a little bit. Yes?
Can there be a limit where one side is continuous with the other? I mean, if one side is continuous but not included in the other side,
You mean something like this?
Yeah.
Absolutely. Very good question. So this would mean, like the way that I wrote it, that A is included, it's continuous at A, but that it's not necessarily continuous at B. And that could definitely happen. Like imagine that you had some kind of a graph where it started at this point, or maybe even, continued to the left forever or something like that, but there was an open circle for some reason right here. So yeah, you could definitely have that. All right, so let's take a look at this function that we mentioned before. We actually have a function inside of another function, and this wants us to determine the intervals on which x is continuous. So what we're going to do first is we're going to look at the area very inside of the function, and we're going to identify if there's any places that are going to be continuity problems. And there is. There's a continuity problem here. What's the problem? 0. X can't be 0 on there, right? Now cosine can have anything inside of it. That's great, but the 1 over x has the problem. Agreed? So we actually have this issue. We have to say that, well, let me write it this way. I'll write out a few words. So cosine of x is continuous everywhere. But 1 over x, as we've said, is not continuous at x equals 0. So when we combine them together, we have to take into consideration both of those features and be as restrictive as we need to include all the pieces of information. So our function f of x, which is the cosine of 1 over x, is continuous, And now remember how the directions said to say it. It said to say it on what interval? So I can't say is continuous x not equal to 0. That's not how it asked me to say it. It wants me to say it in terms of an interval. So do you remember how we would write the interval that excludes 0? Okay, and I need some notation surrounding this. Yep, I need some parentheses here. So we always use parentheses around the infinities and negative infinities because they're not a value, it's a concept, okay? You can't equal infinity, in other words. And then we're using the parentheses around the zeros to show that we are excluding the 0 as well. So this is the notation that we would be wanting to use. Any question on this one? Alrighty. Let's take a look at a context problem of how some of this works. We're going to determine the constant value of c, and there is only one c in the problem, that makes the function continuous for all x. And then it wants us to give a rationale for why such a function should be continuous. And here's our context. So suppose that a state's income tax code states that the tax liability on X dollars of taxable income is given by this equation. So let's just talk through a little bit about the splits in what's going on, okay? So they've sort of divvied up the different X values over here in piecewise form, right? It tells us that X dollars, the tax liability on X dollars, so X is the number of dollars that somebody's making. Everybody good so far? So the first line of my equation says X is less than or equal to 0. Okay, that means you didn't make any money. Obviously, you didn't make any money, you're not going to pay any taxes on it because you didn't make anything. Okay, so that's what that first line says, that there's really nothing that happens if you have a value that's 0. And to be honest, you can't really have a negative, right? It doesn't really work either in terms of income. The second line says that you're going to be going between X equals 0 and X equals 10,000. So this is somebody that makes less than $10,000 a year. Okay, good with that so far? So if you make $9,000 a year or $4,000 a year or $40 a year, you're in this middle line. Okay? The third line says this is for X is greater than 10,000. So this is somebody making more than $10,000 a year. And if that's you, then you're in the third line of the equation. Okay. Everybody good so far with understanding how they're breaking this apart? All right, so obviously there's no problem on the first two lines being continuous. And the reason I can say that is because if you'll take a look and you have X equals 0, and if you plug in here X equals 0, do they both equal 0? Yeah, they both equal 0. So the two one-sided limits are the same. They both approach maybe at different ratios like this or something like this, but they both approach 0 from both directions, right? And one of them actually equals 0. Is it the first line or the second line that actually equals 0? First one. How do you know? Yeah, it has the notation with the equal sign. You guys see that? So that's actually the one that's telling us, like if we were doing a graph for it, where to fill in the circle. And it's the same on both sides, the first line or the second line, but it's the first one here that's actually telling us to fill in the circle. Now, the second one right here is a little trickier because it doesn't actually tell us what happens at 10,000, right? So if you're doing 10,000, do you plug it into this? I mean, if somebody makes exactly $10,000, which one of these places should we be plugged into? Because I'm going to tell you what, it's not 0, right? That'd be really tricky though too. Like if you found out, like if I make exactly $10,000, I pay no taxes. Kind of cool, but be tricky. Like to make sure you made exactly $10,000. So it's going to be one of the two bottom lines, right? And whichever one it is, shouldn't it match? I mean, wouldn't it make sense? Wouldn't it be awkward? Let's say it this way. Wouldn't it be very awkward that if you made $10,000 and you're on line 2 and you make $10,001 and you're on line 3, and somehow between $10,000 and $10,001, your tax burden is so much higher? That'd be awkward, right? This is what it's talking about when it says give a rationale for why such a function should be continuous. Well, it should be continuous because when you make $10,000 and you change to making $10,050, there shouldn't be this great disparity either up or down, right? It shouldn't be all of a sudden I made $50 more and I've got twice as much taxes to pay, or $50 more and I have half as much taxes to pay. It should be more, but in some sort of a fashion that makes this continuous. It makes sense. Do you guys understand what this is talking about for the rationale part? Is that okay? It's going to ask you a question similar to this with a rationale thing on a problem in your homework, right? So that's why I'm belaboring the point at this point. However, now it wants us to actually figure out what C would have to be to make that work. All right, so here's the way that we're going to think about that. What we want to do is we want to find the limit of this function, t of x, as x approaches 10,000 from the right, or actually I'll do left first, and then the limit of my function t of x as x approaches 10,000 from the right. We want these two things to be the same. That's what makes it continuous. Agreed? It's got to actually meet at the same place if I used 10,000 from both directions, or I approached 10,000 from both directions. So what does that look like? Well, we talked last time about limits being able to just be plug in the value as long as you're actually able to do it, right? And we talked about sometimes that meant factoring first, and sometimes it might not. So on this one in particular, if you take this particular equation, what this is telling you is that which one of these equations, the second one or the third one, is the 10,000 from the left? It's the second one. So what this is telling us is that I can take my second equation and I can plug in 10,000. And this is the value that we're going to get close to if we approach x equals 10,000 from the left. What is this number? 1,400? Does that look okay to everybody else? Awesome. All right. What about the second one up here, this second blue line that says 10,000 from the right? What am I going to do there? It should be equal to 1,400, right? Okay, so we're going to make, that's going to be my next step after this one. What am I going to do before I set it equal to the 1,400? Yeah, I'm going to plug in 10,000 to the third equation, right? Because this right up here says that I'm approaching 10,000 from the right-hand side. That means values that are slightly bigger than 10,000. Well, this right here says these are values that are bigger than 10,000. So I'm going to plug the 10,000 in for this x right here. So I've got c plus 0.21 times my 10,000 here. So this is c plus something. What is 10,000 times 0.21? What is it? 2,100, right? Okay, and then is it Akil? Is that right? Ayub. Akil's your last name, isn't it? Okay. Ayub. Then this is where what Ayub said is going to come into play. These two are supposed to be the same. Because if the limit really exists, the limit has to be the same from both directions. So what we're trying to say, oh, and I ran out of space, I'm sorry. I'll use this bottom of the screen, is I'm trying to say that the limit of t of x as x approaches 10,000 from the left equals the limit of t of x as x approaches 10,000 from the right. Well, I found each of those limits, right? The first one was 1,400. The second one was c plus 2,100. So am I able now to figure out what c should be to make this actually work? Sure. What would c be? Negative 700 is correct. Yeah. It's not a very good zero. Let me try that again. This is negative 700. Okay, so that's part of the directions. It said, let's see, where to say it? Yep, determine the constant c. We did that. And then it said to give a rationale. So I've said a lot of language outside of what my rationale would be. I'd like for you to write down some version of that on your paper. Why in the world should this be continuous? Why does that make sense? Note one other thing here, too. The way it's actually written in here, we need either line 2 or 3 to include the 10,000. Because in order for this to actually be continuous, the function value is supposed to exist. And right now, that is the way that this is written in here, neither one of these has that equal value, does it? that's actually something that would have to be edited inside of this particular problem to make this really work. So I mentioned that just in case you're thinking, oh, wait a minute, that doesn't, it technically doesn't work the way that this is phrased. That is definitely sort of an error in the way that the problem is set up. One of those should say equals, okay? But go ahead and take about 1 minute and write down a rationale for why in the world this should be continuous. It should have something to do with the fact that when you change from $10,000 to $10,001, your tax should change slightly, not drastically, down or up. And that's the kicker, right? That's kind of what's going on. So write down a sentence or two that describes why in the world that should be the case. And then we'll look at the intermediate value theorem, which will hit a little bit more on this idea too, actually. Yeah, back on this previous slide, if you'll take a look at the second line of the piecewise function, and it has less than 10,000, and the third line has greater than 10,000, one of those needs to have equals 10,000. Otherwise, what this is actually saying is that if I've got $10,000 that I've made, I don't know where to plug it in. And while it should be the same as on the second line and on the third line, I need to know which one I'm actually supposed to be using to evaluate it. I need an actual place where it's supposed to be evaluated. Without the 10,000, it's actually got like a hole in the graph is what it really has. And we're not supposed to have a hole in the graph if it's continuous.
So there's not,
it doesn't actually work the way it's written in here specifically. So if I was doing this problem and the book said this, just like exactly the way that this was written, it would be appropriate to be concerned with the fact that this actually, even letting C equal negative 700 doesn't make it continuous. I still have a continuity issue until I put an equal sign on either line 2 or line 3 by the 10,000. Once I have that, then I'm good.
So it would be a D and E?
Yeah, it would, technically, the way that it's written. I think that the example that you're going to do in your homework doesn't have that problem with it. It doesn't have a place where it's simply missing the equal sign. And this might be a typo on my part, but this one originally I did get from the book, so it also might be that the book has a typo in this. Somebody's got a typo. Well, we'll say it's me. We'll say I just screwed it up.
So how would we write the
something like what we wrote here, that C equals negative 700, and the second or the third line also needs to have an equal sign. Yeah, it needs to say less than or equal to or greater than or equal to.
So we're solving for C.
We're solving for C. That is the goal in the problem, is to solve for C. Let me kind of mention, I see some of you are still writing, which is fine, but the problem that you have like this in your homework, you're actually going to be solving for 2 letters. So on this one, we only had to solve for C because C is the only letter here that's not the variable x, right? There's only one letter in the problem. And we had this sort of nice feature that there was no problem with continuity on line 1 and line 2, right? Because they were already continuous, because if you plug in 0 to both of them, it works. That's great. Well, the problem that you have in your homework actually has 2 letters that you're going to solve for. So you're going to have to look at line 1 and line 2 and compare them. And then after you figure out that value, you're going to have to look at lines 2 and line 3 and compare those. So you're going to have a double comparison to make, actually, on your homework problem. All right, let's take a look at the intermediate value theorem. Was there any more questions about that one before I go on? Okay. Intermediate value theorem is actually something that you have seen before, and you know it's true. And once I draw a picture, you're going to be like, oh, yeah, well, obviously. Okay? So notationally, here's what it says. Suppose that f is continuous on a closed interval, and w is any number in between the y value at a and the y value at b. Then there must be an x value between a and b, called c. C has to be between a and b, for which the function value is something between, or is equal to the w. Notationally, that just sounds awful. Let me draw you a picture, and you're going to go like, oh, that's all that meant? So let me show you. Here's what this is saying. There's someone out the door? Is that what we're hearing? Lawnmower? Okay, got it. All right, so let's say that we have this particular graph. And here is my A value, and here is my B value, and the graph is continuous between A and B. Everybody good so far? All right, so it looks like from my graph, those are my particular points at A and B. So over here is the Y value at A, called f of A. And here is the Y value, roughly, at B, called f of B. So that's the very first sentence. The function is continuous between A and B. F of A and f of B are the Y values that go with them. The next thing it's telling us is that W is between A and B. So it's saying that I've got some number W in between. What this is saying is that if you think about it over here in the graph itself and you trace across here to whatever place you are, that value that I hit had to actually be somewhere between A and B down here. And they're calling it C. That there's some X value that corresponded to it. Okay? So think about what would have to happen if that weren't true. Well, if that weren't true, then when I went from W straight over, I would have had to have a hole in the graph. Can I have a hole in the graph? No, why not? Because it's supposed to be continuous. If I didn't have a hole in the graph, in fact, I might have a jump in the graph, right? I could actually have a break so that there's a place that's a gap. Can I have a gap? No, because it's supposed to be continuous, right? Those were the conditions upon which this was set up, is that it was continuous. So I can't have any of those holes or gaps. So you look at this and you're like, well, yes, obviously then there must have been an X value that went with that Y value, right? Okay, so let's take a look at an example. I'm sorry, there's a corollary first for that, and then we'll look at an example of the intermediate value theorem. This corollary is probably the cleanest version of the intermediate value theorem. This one says, suppose that f is continuous on AB, and f of A and f of B have opposite signs. So I'm going to draw a picture for what this is telling you. So I've got the same picture I had before, except that the graph actually has some of the values below the x-axis, and some of them are above. So here's A, here's B. So over here, f of A is negative, and up here, f of B is positive. So far, so good? F of A and f of B have different signs. One of them is positive and one of them is negative. What this corollary says then is that there's some place that I had to have crossed the x-axis. Yeah, I mean, right? I mean, how else could I draw it? Is there any possible way that I could go from a negative value to a positive value and not cross through 0? And the answer is no, that's not possible. Right? That's just fact of life, not possible. Had to have crossed through 0 in order for that to happen. Now, there's a practical example of that in terms of driving in your homework. And so I'll leave that for you to see and take a look at. And it's a little bit tricky, but most of you probably do drive or have at least ridden with someone who has. So think about when you're looking at this problem, this idea of positives and negative and how that actually works in terms of a car and driving when you get to that point. Let's do just an equation point value on how this works. So this one says to use the intermediate value theorem to verify that f of x has a 0. Okay, if that language is not familiar or you haven't seen that in a while, a 0 just means an x-intercept or a location where y equals 0, or it crosses the y-axis. All that means the same thing. Sometimes you hear the word root. They'll call it a root, which is not great language because we use the word root for so much, but sometimes you'll hear it called that. So it says to use the intermediate value theorem to verify that it does in fact cross the x-axis. So what does that mean? Well, let's take a look back at the conditions, and in particular, because we're talking about it crossing the x-axis, we can look at the corollary itself, okay? Because the corollary talked about x-axis stuff specifically. So I have to be able to satisfy the conditions. The first condition is that it's supposed to be continuous, right? That's the very first condition. So I have to make sure that when I look at this function, it's continuous. So condition number 1, it's continuous. Is it? It is. Do you know what we can state is the reason that we know that this function is continuous? It's a polynomial function, isn't it? Back over here, so I can get to the right one. Theorem 4.1 talked about polynomials. It says polynomials are continuous everywhere. So anytime we have a polynomial, or a sine or a cosine or a radical kind of, anytime we have one of those, we automatically, it's like we get it for free. This is continuous because it's a polynomial. And do you have to write down the issue about continuous? Yes. You need to know that this is continuous, because if the function's not continuous, nothing else works. If it's not continuous, can I have a hole in the graph? Yeah. If it's not continuous, can I have a jump in the graph? Yes. And if I have a hole or a jump in the graph, do I have to cross the x-axis? No, I don't. So this is really important, that it really is continuous. All right, the second thing is, it says that f of a and f of b have to have opposite signs, right? So, what are my a and my b in this particular scenario? 2 and 3, you got it. So these values right here are sort of the values that I'm supposed to be considering. In particular, what I need to do is I need to figure out what in the world is f of a, or f of 2, and what is f of b, which is f of 3. So, what is f of 2 in this function? Right, it's 2 squared minus 7, which is negative 3. And what is f of 3? All right, so this is 3 squared minus 7, or 2. And what do you notice right here? Opposite signs. These are, in fact, opposite signs. Okay, so let's go back over here. Continuity, we've got that. Opposite signs, we have that. So what does this corollary say has to happen then? Then there is at least one number, C, between A and B, that's between hour 2 and hour 3, where that value equals 0. And that's exactly what we were trying to say happens. So this is sort of the conclusion. Sometimes you'll see these 3 marks right here, and this is read, therefore. Therefore, now I have a conclusion I can state. My conclusion is by, and you can call it by the intermediate value theorem. You could say by corollary 4.2, whichever one. By corollary 4.2, there is a value C between 2 and 3, not A and B. We've actually got 2 and 3 in our problem. Between 2 and 3, where f of C, that is that y value, equals 0. The corollary says that. And it says that because we checked all of the conditions before it that allowed us to make that claim. Any questions on that? We're all good? All right.